Take a quick look at the device you're using to watch this explainer right now. Whether it's a sleek laptop, a powerful desktop, or even a server powering the cloud you're streaming from, it's wild to think, but there's a very good chance its fundamental brain architecture traces its lineage directly back to a single revolutionary chip released in 1978. I'm talking about the Intel 8086. Today we're going to unpack how this single microprocessor didn't just advance technology, but literally laid the bedrock for the modern x86 computer architecture we still rely on today. So here's our roadmap for this explainer. We'll start with the birth of the 8086, move into the 16-bit revolution, and then take a peek inside the CPU kitchen. After that, we'll cover memory, segments, and buses, followed by the lasting x86 legacy. Let's get right into it. Section 1. The birth of the Intel 8086, the origin of the x86 family. Before this era, computers were these massive room-sized machines that cost an absolute fortune. We desperately needed a way to shrink all that immense calculating power down into something actually manageable. And, well, the solution to that was the microprocessor. If you think about your computer like a human body, the microprocessor is absolutely the central brain. It's this tiny electronic chip doing all the heavy lifting. It performs the calculations, follows the instructions, and basically bosses around every other part of the machine. Just look at the sheer speed of innovation happening here. Back in 1971, Intel rolled out the 4044, which was the first 4-bit commercial microprocessor. Literally 1 year later, they hit 8-bit with the 8008. By 74, the 8080 was already powering early computers. But this relentless, unstoppable drive for faster speeds and bigger memory for personal computers led straight to 1978 and the Intel 8086. This was the very first 16-bit processor, and honestly, the true foundation of the modern PC. Moving on to Section 2, the 16-bit revolution, doubling the power. We hear this term 16-bit thrown around constantly, right? But what does that actually mean for the computer's performance? It all comes down to throughput. Imagine data as water flowing through a pipe. An 8-bit processor has a pipe that moves, 8 bits of data per trip. The 16-bit 8086 upgraded that to a much wider pipe, moving 16 bits at a time. Or let's use a classroom analogy. Picture 2 students handing out exam papers. The 8-bit student carries 8 papers at a time, while the 16-bit student carries 16. That 16-bit student is finishing the exact same task twice as fast. It was a massive, massive leap forward. And to make all that 16-bit magic actually happen, they had to pack 29,000 transistors onto a single tiny chip. The 8086 operated at a clock speed of 5 to 10 megahertz. To visualize what clock speed means, think of a teacher clapping their hands to keep a rhythm going. Every clap tells the students to perform their next action. At 5 megahertz, that internal clock is clapping 5 million times every single second. For the time, it was blistering speed. All right, Section 3. Inside the CPU kitchen, the two halves of the 8086. So how does this microscopic marvel actually get work done? Let's crack open the chip and think of it like a really busy restaurant. The 8086 is brilliantly split into 2 main parts. Over on the left, we've got the Bus Interface Unit, or BIU. You can think of the BIU as the delivery person or maybe a librarian. Its whole job is to travel out to the memory, fetch instructions, read data, and figure out the memory addresses. Then on the right side, we have the Execution Unit, or EU. This is our chef. The chef never actually leaves the kitchen. Instead, they just take the ingredients the BIU delivers and they cook them, doing the addition, subtraction, multiplication, and making all the logical decisions. Now think about it. A good chef isn't going to walk all the way across the kitchen to the pantry just for a pinch of salt, right? They keep a spice rack right next to the stove. Inside the 8086, that spice rack is made up of registers. These are tiny, insanely fast storage boxes built right into the CPU. We've got the AX register for main calculations, BX for base addresses, CX acting as a counter for loops, and DX for extra calculations. These let the execution unit work at lightning speed without constantly waiting on slower external memory. Next up, Section 4, Memory, Segments and Buses, organizing the computer's workspace. Because honestly, even with a super fast chef and a dedicated delivery person, a restaurant still needs a well-organized pantry and clear roads for deliveries. So to manage its external memory, the 8086 uses something called segmentation. Imagine this external memory is a big school building. Instead of just dumping everything into one giant chaotic hall, it's divided up into dedicated rooms. The code segment is like the teacher's office. It stores the strict program instructions. The data segment, that's the classroom cabinet holding your variables. The stack segment is basically your backpack for temporary information, and the extra segment is exactly what it sounds like, an extra storage room. This setup kept the 8086 incredibly organized and efficient. Let's take a closer look at that backpack, the stack segment. The stack operates literally exactly like a stack of plates in a cafeteria. The last plate you put on top is the very first plate someone takes off. In computer architecture, we call this last in, first out, or LIFO. You push data onto the top of the stack to save it, and you pop it off the top when you need it back. Simple, but highly effective. And to connect our CPU kitchen to all these memory rooms, we need roads. In computing, we call these roads buses. The data bus is your delivery truck, carrying the actual package, the information. The address bus is like the GPS. It tells the processor the exact house address in memory where that data lives. And the control bus sends the commands, telling the system to do things like read or write. Thanks to a 20-bit address bus, the 8086 could navigate up to 1 entire megabyte of memory. Let me tell you, in 1978, that was an absolutely huge deal. Section 5. The instruction cycle. Seeing the brain think. We've got our chef, our delivery person, our spice rack, our pantry, and our delivery roads. Now let's watch this electronic brain actually put it all together. Every single action a computer takes is broken down into a 3-step instruction cycle. Step 1 is fetch. The delivery person, the BIU, goes out to memory and fetches the recipe. Step 2 is decode. The chef, the EU, reads that recipe and understands that it means, say, addition. And step 3 is execute. The chef actually mixes the ingredients together and adds the numbers. Fetch, decode, execute, over and over again, millions of times a second. But the 8086 speeds this whole cycle up with something brilliant, an instruction queue. Instead of the chef just standing around waiting for the delivery person to fetch the next recipe, the BIU can fetch up to 6 bytes of instructions in advance. It creates a waiting line. This means the chef always has the next order ready to go. Such a simple queue, but it was an absolute time saver for this architecture. Which brings us to Section 6, the lasting 86 legacy, from 1978 to today. Let's zoom out from the microscopic operations of our little CPU kitchen and look at the sheer global impact of what Intel created here. The 8086 and its core concepts didn't just stay in some R&D lab, they literally changed the world. Its sibling, the 8088, which had the exact same internal architecture, powered the famous IBM personal computer back in 1981. But it went way beyond PCs. This architecture ran cash registers, life-saving medical equipment, and factory automation systems. Just to give you an idea of the reach, a banking terminal all the way in Tanzania used an Intel processor with this exact architecture to read account numbers, calculate balances, and print receipts. It was quite literally everywhere. Just look at this staggering contrast. The 8086 was 16-bit. Today's processors are 64-bit. We went from 5 megahertz to screaming speeds up to 6 gigahertz. From 1 megabyte of memory to billions of gigabytes. And from 29,000 transistors on a single core to literally billions of transistors spread across 24 cores or more. But here is the absolute most crucial point. Despite these astronomical upgrades, both processors still rely on the exact same foundational x86 architecture. They both fetch, decode, and execute instructions using registers, memory, and buses. It's the same DNA. The Intel 8086 is, without a doubt, the undeniable ancestor of almost every PC we use today. We've taken a journey from a single chip with 29,000 transistors acting as a simple chef in a kitchen to supercomputers with billions of transistors shaping our modern reality. So as you look at the device sitting in front of you today, it leaves us with one pretty profound question. If this is what happened in just the last 40 years, what on earth will the next 40 years of computer architecture look like?